lecture for Chapter 2 of Conceptual Physics, 12th edition by Hewitt. In this chapter, we're going to introduce our first significant physics concept, which is Newton's first law of motion, known as the law of inertia. All right, so our topics are going to be Aristotle's idea of motion, which was proven to be wrong, how Galileo laid the groundwork for Newton's first law of motion, the ideas of net force, and introducing something very important called a vector, the equilibrium rule, support force, which is a particular type of force, equilibrium, and the consequence of the moving Earth and how to think about that. All right, so over 2,000 years ago, Aristotle's classification of motion was that there was such a thing as natural motion. This basically said that every object had a proper place. Think the four elements, right? So the earth element and things that are heavy in the earth element, like stones, well, they wanted to return to the ground because earth elements attracted earth elements and so on. Okay? All right, so that was the idea, right? Puffs of smoke rose because they were full of the air elemental. All right, so that idea persisted for quite some time. All right, so it included straight up or straight down for all things on Earth. All right, and that definitely matched up the everyday experience, right? If you weren't taking a physics class, if this was 600 years ago or 1,200 years ago, then yeah, you would notice things fall straight down. That makes sense, right? Or even if you some things go straight up. Okay. However, beyond Earth, motion is circular, right? So that would explain the motions of the stars in the sky on a given night. That would explain the motions of the planets, right? So, these wandering stars, and that's it. And of course, even the moon, right? So perfect circles up in the heavens, straight up and straight down here on terra firma. Okay. There was also violent motion produced by external pushes or pulls, right? You could blow something up, right? Release that energy, and then that could create violent motion. That was a different classification, all right? But you see here, there's a lot of messy classifications. Why is it that things up out of Earth behave differently than things on Earth? Why are there different rules for the planets than there are for Earth? Why are there different rules for violent motion as compared to natural motion? That seems pretty arbitrary, and indeed it was arbitrary. But to recognize what's arbitrary and what's not, that's a difficult task, okay? And it wasn't until scientists of much later up until the 15th century, the 1400s, that we finally get some new ideas revealed. So Galileo demolished Aristotle's assertions in the 1500s. Galileo's discovery: objects of different weight fall to the ground at the same time in the absence of air resistance. Okay, so that means that there was something universal here. In a vacuum, a feather and a rock would fall at the same rate. Okay, so it's not. The rock isn't fundamentally different. Instead, there's a universal attraction. The idea of gravity, the notion of gravity was coming to play here. A moving object needs no force to keep it moving in the absence of friction. So if you have a really smooth surface, think like an icy lake, and you push something, it'll keep moving for a very long time because there's so little friction. If you were to eliminate that friction completely, which of course we now know is possible in deep space, then something will just move forever. Okay, so now we have some modern ideas. A very, very important word in this class is the word force. Okay, a force is simply a push or a pull. Inertia is not a force, doesn't have the same units as force. We'll talk about the units of force later. It is instead a property of matter. You see that there? It's a property of matter. Okay, it depends on the amount of matter in an object, its mass. The unit we're going to use for mass is the kilogram. You've probably heard of things being weighed in kilograms, okay? It's not actually a weight, it's a mass. Although those terms in everyday language get kind of interchanged, weight versus mass. We'll distinguish between the two in this class. There is an important distinguishing factor between them, okay? And we'll talk more about this unit later, but the unit of force is the Newton, okay? Uppercase N for Newton. Notice I'm putting units in parentheses. Balls rolling on downward sloping planes pick up speed. Balls rolling on upward sloping planes lose speed. Well, yeah, it's common sense, right? We know that. So a ball on a horizontal plane maintains its speed indefinitely, okay? Its inertia means that if nothing acts on it, then it will just keep going forever. It requires a force to cause something with inertia to change its motion. And everything that has mass has inertia, okay? If a ball comes to rest, it is not due to its nature, but due to friction. An external force, a force acting on that object that has mass, thus has inertia. Okay, this ball has inertia. So the use of inclined planes for Galileo's experiments helped him to do what? Okay, pause the video here and think about the answer. Discover the property called inertia, the fact that objects will continue in motion unless acted upon by a force. Okay, and just a good reminder, because a lot of people don't really kind of understand what inertia is. It's a property of matter. So every object continues in a state of rest or of uniform speed in a straight line unless acted on by a non-zero net force. So Newton came one generation, if we're thinking history-wise, later than Galileo. He was actually born the year that Galileo died. And in his kind of further clarification, further synthesis of the ideas proposed by Galileo and the scientific peers of Galileo, he came up with this beautifully concise idea that takes inertia, and instead of just kind of labeling it, saying, hey, it's out there, it's important, he puts it in the context of motion exactly. Every object continues in a state of rest or of uniform speed in a straight line unless acted on by a non-zero net force. There's a bit to unpack there. What is net, right? Well, net means total, right? It's a word that we use in mathematics and physics to mean total. It's a sum of many things. So if I have a push from one direction and a push from the other direction, then the net would be the sum of those two pushes, okay? All right, okay? Uniform speed means it's not slowing down or speeding up, and a straight line just means it's not curving, because curving does require force, right? You can't turn for free. Okay, so in order to kind of further understand the idea of net force, we have to introduce the idea of a vector. What is a vector? Okay, well, it is a quantity whose description requires both magnitude, that's how much, and direction, which way. All right, so a vector is represented by an arrow. All right, and the length of this arrow, so that's from the tail here to the tip up here, the length of that arrow is its magnitude. Okay, so it could have a length of 5 newtons, 5 meters per second, 5 meters per second squared, right? These are many common vectors we're going to see, okay? And so that's its length, its magnitude. And its direction, well, it's pointing at an angle above the horizontal. That might be the way we think about its direction. Or we could think about its direction as a right triangle, right? So if this is a force, F, then there could be components of that force. An X component, because that's horizontal, and X is for horizontal, and a vertical Y component. Okay? And that, in that way, we'd be describing the direction of the vector, because we could say, oh, well, its X component is shorter than its Y component, so that means that it points up. Okay? Up, and in this case, to the right. Okay? Represented by arrows, can be usually drawn to scale, so the length matters. Okay, that's what a vector is. That's the pictorial representation of the mathematical quantity called a vector. All right, as I said before, the length represents its magnitude, and the arrowhead shows its direction. Force, velocity, and acceleration are the big vectors we're going to see. Because there's certain things in this class, many things that aren't vectors. Time is not a vector. Turns out energy is not a vector. But there are some very important ones, especially in the early chapters, force, velocity, and acceleration. Many of you will be glad when we move on and leave vectors behind, because the fact that we have to worry about angles and components and right triangles can be a bit of a bear, right? Okay, mostly we're just going to be using the Pythagorean theorem, however. Okay, and basically exclusively. Net force is the combination of all forces that act on an object. Example, two 5-Newton pulls in the same direction produce a 10-Newton pull, a net force of 10, because it's 5 plus 5, right? You can see that here. They're both pulling in the same way, so when you combine them together, you get something that's twice as big as either one of them. On the other hand, if the pair of 5-Newton pulls are in opposite directions, well, they obviously cancel out, and it's not going to go anywhere. So in that case, it would be 5 minus 5, because in this case, we're calling the positive direction to the right. Now I could call the positive direction to the left, and that would just make this 5-Newton force negative. So it doesn't matter which one you call positive, you just have to be consistent. Okay? But the important thing is that here we'd have 5 minus 5 equals 0, or of course here we had 5 plus 5 equals 10. Okay? That's the idea of vector addition, at least when the vectors are all in a straight line like this. A cart is pulled to the right with a force of 15 newtons while being pulled to the left with a force of 20 newtons. The net force on the cart is, pause, make sure you can answer this, 5 newtons to the left, right? Because the bigger force was in that, so we essentially would have 20 minus 15, which would give us 5. you could also think of it as 15 minus 20, negative 5, and call the left the negative direction. Okay? What is the net force acting on the box? Okay? Take a look at that. Make sure you can answer it. It's further practice. All right? We got this one, right? 5 newtons to the right. Right? You can see it. Just adding them up. And you can kind of see, and you can imagine the vectors too, right? I take the 10 one, and then I take the 5 one, and then that cancels out all this. So all that's left is one that's half as long. And that's the remaining 5 newtons to the right. So a vector quantity has magnitude and direction, is represented by an arrow, right? Scalar quantities, on the other hand, this is just a summary, right? So we already knew all this about vectors. But a scalar quantity, on the other hand, just has magnitude. It does not have direction. No direction. Okay? Mass, volume, speed are directionless, because the speed of your car does not have direction. When I say I'm driving 60 miles per hour, that's not a vector. If I said I was driving 60 miles an hour pointing towards the north, well, that is a vector, right? Kind of a clunky one to describe in that way, but that would technically be a vector. But speed is not, okay? In fact, you can think of speed as the magnitude of velocity. Speed is the magnitude of velocity. A resultant is the sum of 2 or more vectors. For vectors in the same direction, you add them arithmetically. That's what we've been doing. In the previous 2 examples, the quick checks that we just did, that was arithmetic addition. We just, 5 plus 5, or 5 minus 5, or 10 minus 5, right? That was because they're all in the same plane, right? They're along the same line. For vectors in opposite directions, we subtract them arithmetically, okay? Right? Or we could just add the negative. 2 vectors that don't act in the same direction, we have to use the parallelogram rule, okay? And to the extent that we're going to use that in a class, we could have vectors that point at right angles to each other, in which case we'd use the Pythagorean theorem. Again, I'm not going to be asking you to take components. You're not going to have to multiply by any cosine or sine of any particular angle, and make sure your calculator's in degree mode or any such of that. Instead, you just have to use the Pythagorean theorem. Okay? Case in point. Referring to the figure, which of the following are true statements? Okay? Take a minute. Make sure you can do this one. And if you can't, that's okay, because then you know what you need to work on. Okay? All of the above are correct. The 50 Newton is the resultant of 30 and 40. The 30 Newton vector can be considered to be a component of the 50 Newton vector, and the 40 Newton vector can also be considered to be a component of the 50 Newton vector. In fact, we would refer to the 30 as the vertical component and the 40 Newton as the horizontal component, right? Because one points up and one points to the side. Okay, where does the 50 come from? Well, the 50 comes from the fact that 50 squared equals 30 squared plus 40 squared. I didn't exactly do that in my head. I just know that one because if you divide all of them by 10, 5 squared equals 3 squared plus 4 squared, because 4 squared is 16, 3 squared is 9, 16 plus 9 is 25, the square root of 25 is 5, right? Multiply everything by 10 and you get 50, 30, and 40 instead of 5, 3, and 4. If you recall from a math class, it's called a 3, 4, 5 triangle, right? Famous type of triangle. All right. Nellie Newton hangs from a rope as shown. Which side has the greatest tension? There are 3 forces acting on Nellie. Her weight, okay, which we call mg, okay? More on that later when we talk about Newton's second law, but we can refer to her weight as mg. I know it probably seems kind of weird. Why do we call it mg? But you'll become clear in the chapter on Newton's second law. A tension in the left-hand side of the rope and a tension in the right-hand side of the rope, okay? So there'd be some tension here, right? And then there'd be a tension here, okay? Right? And that is the total amount of force, okay? And in fact, if I was to draw them to scale, right? So here, let's do this a bit better, okay? I'm just going to do something real fast. Oh, I did the wrong thing. There we go. I wanted to erase it, okay? So here, if you look at the length of this vector here, and this one here, this dotted one is purposely drawn to be the same length. And so there's a right triangle here, okay? There's a right triangle because you can take, and there's a triangle and there's a right triangle, but you could take a length along this side. See how it's parallel to this rope, right? And this is meant to be like a scale, like a fishing weight scale. And then you could take another one that goes along this rope. And then if you take those 2 vectors, you can add them up like so, to be the length of the total vector that's equal in magnitude to mg, her weight. Okay, because the two tensions together have to support Nellie, otherwise Nellie falls. All right? But because the ropes are not at the same angle, the tensions are not equal. Okay, the next slide gets into it in some more detail. Because of the different angles, different rope tensions will occur on each side. Nellie hangs in equilibrium. Okay? Equilibrium means she is not accelerating. We'll talk about acceleration in the very next chapter, even before we talk about Newton's second law. But it just means she's at rest in this case, because you can be in equilibrium and coasting at the same speed, or in this case, you can be in equilibrium and be at rest. Basically, everything that's built to be stable is in equilibrium. Or in this case, Nellie hanging and stably hanging is in equilibrium. Okay, so our weight is supported by the two rope tensions, adding vectorially, right, as opposed to arithmetically, to be equal and opposite to her weight. The parallelogram rule shows that the tension in the right hand is greater than the tension in the left. What's a parallelogram? This is a parallelogram, right? It's just a rectangle that's tilted a little bit. And when you tilt it, you can clearly see that one side of the rectangle is this force vector, and the other side of the rectangle is this force vector, and the rope that is a steeper angle inherently has greater force. It's holding up most of Nellie. Okay? Right. That's the parallelogram, because we made a square out of it. And that square then can be split into two triangles, both right triangles. All right? So a little bit of geometry. I promise you no trig, but I didn't say no geometry. Okay? So the equilibrium rule, an example. A string holding up a bag of flour. Two forces act on the bag of flour. Tension force, okay, in the string, right? Just like there was tension forces in the rope that held up Nellie. That's what we call that type of force that holds something up. And a force due to gravity that acts downwards. Both are equal in magnitude and opposite in direction. When added, they cancel to zero. That's what equilibrium means. It means that your forces sum up to zero. So the bag of flour remains at rest. The vector sum of forces acting on a non-accelerating object always equals zero. Okay, again, we'll talk more about acceleration, but that just means it's not speeding up or slowing down, and if it's already at rest, it remains at rest. Okay? In equation form, we write it like this. This funky little symbol here is uppercase sigma, and it just means sum. Okay, so this is the sum of forces equals zero. Here's an example of some painters on a hanging platform. The tensions here exactly equal the weight of the platform itself plus the weight of the two painters. Okay, so the three downward forces are exactly equal in magnitude to the two upward forces. The total is zero. We sum up 5 forces in this case, and we get a zero. Okay, so that means that another way to say this is that equilibrium always has a net force of zero. It always has a resultant of zero. All right, so the equilibrium rule, sigma f equals 0, applies to what? Make sure you can answer this. Take a minute. Just vectors, okay? Doesn't make any sense for scalars because its very nature, the very definition of the equilibrium rule relies on directionality. Scalars are just numbers. Doesn't make sense to sum them up to 0 in any meaningful way. Support force is the name given to a force that is upward on an object that is opposite to the force of gravity. So unlike tension that points upwards opposing gravity and holds you in place and wants to stretch out a rope or a string or a cable or whatever is hanging, so a support force pushes up from the floor or the tabletop or the couch or the chair, right? The other name for the support force is called the normal force, not because it's so regular or something, but because normal is a mathematical term that means perpendicular, and because it's perpendicular to the surface, we call it the normal force. But support force is more descriptive. Example, a book on a table compresses atoms in the table, and the compressed atoms produce the support force, because it comes from somewhere, okay? All forces come from somewhere. That's a big picture idea that we won't get to much later. When you push down on a spring, the spring pushes back up. That would be another example of a support force. Similarly, when a book pushes down on the table pushes back up on the book, okay? Every force has an equal and opposite force. That's Newton's third law. That's chapter 4, okay? So again, not right now, but something to look forward to. When you stand on 2 bathroom scales with 1 foot on each scale and with your weight evenly distributed, each scale will read. You probably have a guess, but are you second guessing yourself? Okay, think about it carefully. Have an answer. Pause the video, and then let's see. Half. Split between. Because you think about the idea of the equilibrium rule. There's two support forces that equal 1 gravitational force. So those 2 support forces, since we were told they're even, they have to be 1/2 each. Equilibrium is a state of no change with no net force acting. Okay? Static equilibrium, you remain at rest. Okay? A hockey puck at rest on slippery ice. Dynamic equilibrium is a type of equilibrium where you're just not slowing down or speeding up. The hockey puck sliding at constant speed. Okay, so those are just the particular terms. Dynamic, constant speed. Static, rest. Okay, so make sure you got those terms, you know which corresponds to which. The names are, I think help. All right, equilibrium test, whether something undergoes change in motion. All right, so a crate at rest is in static equilibrium. A bowling ball is in equilibrium when both, right? It could either be moving straight along at a steady speed or at rest. Those both are types of equilibrium. Just one's dynamic and the other is static. You push a crate at a steady speed in a straight line. If the friction force is 75 newtons, how much force must you apply? Think about it. Think about the equilibrium rule. Steady speed. You know this. Okay, take a moment, answer it. 75. You have to equal the friction. Okay, if your pushing force is greater than the friction, the crate would be speeding up as you pushed. Okay, now Copernicus proposed that Earth was moving, circulating the sun. Right? Wow. Right? That was the Copernican revolution, it's called, right? The heliocentric model. Finally, the Earth wasn't the center of the universe. Okay, this idea was refuted by people. One reason it was refuted was because if Earth moved, how could a bird swoop from a branch to catch a worm? Right? Because it seems like the Earth would fly away underneath the bird, wouldn't it? Right? If the Earth is really moving at high speed, kind of like think about that, right? This idea that was probably so hard for people to reconcile. The Earth is flying through space at high velocities. I mean, first of all, shouldn't we all just get thrown off of it? That's crazy, right? And really, people couldn't reconcile it. But the law of inertia totally reconciles this idea. In fact, it probably reconciles it so much that the idea of rejecting the movement of the Earth just because of the idea that the Earth is moving so quick probably seems foreign to us, right? We take it for granted. But the solution is that as it swoops due to inertia, a property of matter, it continues to move sideways at a speed of Earth along with the tree. Because there's no other force acting on the bird, right? The bird is going to continue at whatever speed it was at on the branch. So sure, the tree and the branch are flying through space at high speed, just like Earth itself as it orbits the sun, right? Thousands of miles an hour. Really, thousands of miles an hour. But when you jump up, you continue at that speed. It's like when you're on a train, right? When I jump up on a train, I don't go flying to the back of the train at the velocity of the train. So the train's moving along at 50 miles per hour. I don't fly to the back at 50 miles per hour because there's no force acting on me when I'm in the air. There's air resistance, but the air resistance is tiny. So it's not going to make a big difference. I basically land where I jumped, right? Here's an example of not someone jumping, but an object being thrown in a train. You're riding in a vehicle at a steady speed and toss a coin straight upwards. Where will the coin land? Okay, make sure you feel confident about your answer. Okay, pause the video if you need to. In your hand. Okay, doesn't land behind you or in front of you. Now, if the train was accelerating, if it was braking or speeding up, well, that's a different story. But if the train is moving at constant speed, it will land right in your hand. All right. Thank you so much for listening to Lecture 2 for Chapter 2.